Okay, now we're finally on to our first coding exercise, and this one we'll be working on visualizing optimization problems to see for ourselves how optimization problems look like and how to generate those visualizations that help you explore the design and solution space. So if you haven't done this already, please find the link of this deep note notebook in the Udemy platform. The notebook we're going to work on today is the first one, called Visualizing Optimization Problem. You can also start this machine up so that we can run the code directly once we get onto that. In this notebook, we're going to learn how to plot the objective function as a 3D surface plot, and then how to plot the optimum point on the 2D contour plot, and finally plot the equality and inequality constraints as well, and see how they affect the optimal solution. There are going to be some questions for you when you step through this exercise. Feel free to write down your answers or any notes on this notebook as you've duplicated it, so you should now be able to edit and run the code block. And after this video, there's going to be a short quiz based on some of the questions we've come across in this notebook. Then you can select the most suitable answer from your notes in this notebook. So without further ado, let's go into the first part, where we're trying to plot the objective function. This is the same objective function we've seen earlier from the slides. F is our objective function and is a function of x1 and x2. The function being x1 cubed plus 2x1 x2 squared minus x2 cubed minus 20x1. So in order to plot it, which we're going to use Plotly in all of our notebooks instead of Matplotlib, because Plotly is a more modern plotting utility. So we're going to use that. We're also going to use NumPy to handle the mathematical representations of our variables in here. So before we can plot it, we need to first create our design space, which is basically a grid of all combinations of x1 and x2. And then we'll compute the value of f in a direct format where we just plug in x1 and x2 into this particular f equation to see the result. So in our first code block here, we can see that we've imported NumPy as NP. And then here we'll define our x1 and x2 range. Here we say that x1 range is NP linear space, a linear space from -5 to +5 with 50 values in this grid. And then x2 similarly is also a linear spaced grid from -5 to +5 with 50 numbers in it. So once we've defined x1 and x2 range, because they are only one-dimensional, we need to then define a mesh grid so that it is a two-dimensional grid of all of the combinations of x1 and x2. To do that, we do x1 and x2 equals np.meshGrid of x1 range and x2 range. Then with this x1 and x2, we can plug into our equation here, which compute the objective value of all of the location in this particular grid. So we rewrite our equation from here, the objective function, f equals x1 cubed, which is expressed in here in pattern, plus 2x1 times x2 squared minus x2 cubed minus 20x1. So this is how you can evaluate directly the function at all of the different locations in your design space. Now we'll use Plotly to visualize this objective function as a 3D surface. And the way I like to visualize all of our functions or design space is to follow such a procedure or a framework that allows you to do it consistently. So the first step would be to create a figure by calling go.figure. So go is the Plotly interface, Plotly's APIs, or plotly.graphObjects, and then we can use it to create a figure. Then using this figure, we'll define the layout for this particular figure. And then thirdly, we'll plot the data. So this is a simple 3-step framework that allows you to first think about how you want to present the data through the update layout function here. And then finally add in the plot elements you want to plot in this particular figure. If we look closer to the function here, figure.update layout, we have the scene argument here, which takes in a dictionary as the argument. So here we want to specify that this is a 3D figure, so 3D plot. So we have x-axis, y-axis, and also z-axis, and we can also name it x1, x2, and f for our particular problem in here. Then finally, we'll plot the data by using add surface. You can also say add traces to add the different types of plot elements. Once you do figure add surface, you can then specify x1, y-axis, and z-axis what values they should take. In here, we want x1 to be x and x2 to be y, and f is on the height on our z-axis. And we specify color scale as RDBU reverse, so _R. So red will indicate higher values, blue will indicate lower values. And we also can specify the contours in the Z direction to show the contour lines, starting from -400 value, ending at 400 of the value, and with 20 contours levels. And don't forget to run the code block as well. So for this one, we want to run the first code block, and you should see that from the variable explorer here, we now have the F array, x1, x2, and so on. And then for this block as well, we can also run this again, although it already has the pre-generated values, but you can also run it again to see for yourself, or if you have changed the code in any way, you can also rerun it to see what would happen. So now we have our 3D surface. You can feel free to play around with it. You can zoom in, zoom out, and wherever your cursor lands, you would see a tooltip that shows you the x, y, z value for the point on this particular surface. Now, if we scroll down a little bit, here comes our first set of questions to check your understanding. So, for example, what does this surface represent? This surface is basically a surface of the objective function, right? If you think about it another way, what does a point that does not lie on this surface represent? A point that doesn't lie on the surface, this surface right here, is basically a point that the objective equation does not stand. So it's basically not a valid point for your design. So any point on this surface signify a feasible design solution. But which one is the optimal, we don't know yet. That's the only thing that we need to find out. If you want, you can type your notes or answers in here. That goes for all of the other questions as well, just so that you can document or capture your thinking. That would also become handy when you later on go into the quiz, and it will give you some answers, it will give you some choices, and you can see which one is the one that you think is the most appropriate. Now, the second question is about the height. What does the height mean? The height basically means the objective value, right? So for higher position in this surface, it indicates a higher value in the objective. And vice versa, if you have a lower position, it means the objective value is lower. In terms of the colors, because we use a red and blue color scale, a redder point means that the value is high as well. A bluer point means that it's lower, so it also corresponds to the height of this surface. For the lines, they are contour lines, meaning that every point in one line, they share the same objective value. You can also see a instantaneous contour line being drawn when you hover on this surface plot. So this tells you the line that extends from your current cursor position to the end of the surface, where it would have the same value. So it's basically the same height. If you go from here, you can see that the contour line is basically like a slice horizontally that slices all of the points that share the same height. Now, if the goal is to minimize the objective function, where would the solution be? Where would the optimal point be? Earlier, we talked about the optimal point being a valley at the bottom of the valley, so all of the points or all of the neighboring area would be pointing upwards from that point. So we can see that instinctively, you can first look at the blue area, which is over here. You might not be able to see it clearly, but if you zoom in, you should see that this area here, where it's lightly red, is actually a hill. So it actually bumps upward. In here, this is actually a trough or a valley, where it's actually locally taking a downward U shape. So the bottom point over here would be our minimum point, our solution to the minimization problem. Now, we want to plot the solution. We're not going to talk about how we obtain this solution, but let's say you're given the results. We have the minimum point being 2.58 something and the maximum point being negative 2.58 something. To visualize these 2 points, we can create a separate figure, so we don't plot it on the figure we have over here. We keep them separate. Now, first we want to define the minimum x and maximum x in here as the points, and we'll create another figure. Again, step 2, define the layout. We want to define the layout having the x-axis title as x1, y-axis title as x2. Then as a tip, we can also specify a contour object and assign it to a variable CNT here. And this is how we plot a contour in 2D, where we use x and y with their one-dimensional array, so x1 range and x2 range for y. And then in the set argument, we use f again, which is the values. Again, we use our dBu scale, and then we want to show 45 number of contours and also show the labels if you want. Then we can use this function sig.addTrace then with the CNT object here. So later on, we can reuse this again. And then to plot the optimal points, we can use add_scatter, which creates a scatter object and add to the figure. Because x and y here takes in a list or an array, we need to use a bracket to enclose it so that it becomes like an array shape representation. So here we want to plot the 2 points. First one is this here, minimum x and minimum x as well. The 0 means that this is the 0 element in the minimum x tuple. And then we want to take the first element, which is this 0 value in here, because they are represented in x and y, or x1, x2. So this is why we need to write them as such. And then we use a mode of markers and also text so that we can annotate it. We can also define the symbol, the color, size, and the annotation being minimum and maximum according to the order you've put in here. And now you can see that we have successfully plotted the minimum and maximum points in the contour plot in here. And you can see minimum is where the color is blue and maximum is where the color is red, because red indicates high value, blue indicates low value. And next we can look at how to plot constraints. So let's say there is a constraint h being an equality constraint. H is x1 minus x2, that has to be equal to 1.5. If you remember to convert it back to our conventional format, we can move the 1.5 from the right-hand side to the left-hand side, so it becomes x1 minus x2 minus 1.5 equals to 0, so that would conform to the conventional format. Now to plot a constraint in Plotly, we can simply treat it as a contour and specify its type as a constraint. Plotly knows how to plot the constraint using a shaded region representation in that way. So here we can first specify our constraints. H equals x1 minus x2 minus 1.5. This is how we have moved it so that it conforms to a normal format. And again, we're given the minimum point, that is the constraint point over here. Then we'll define a figure and again, define the layout. We want to move the legends to the top right as well for better readability. Then we can update our contour to disable the show labels function because that will probably be too messy. And then we can create an optimum point, that is the unconstrained one, the one that we've seen earlier on the blue side. And then we can create our constraint plot in here that we specify it as a contour graph object. And we give it arguments x1 range and x2 range, the one-dimensional array as x and y. And the set will be our h value, so our constraint value here as specified. And now the contours we can specify to be of a type constraint. And by default, there's also other arguments such as operation and the value. If it was an inequality constraint, then we can change the operation argument. If it's another value on the right-hand side, we can also specify it in here. And then you can specify the name, line color, etc., etc. And then we'll use the same method we've used before, creating a scatter graph object to plot the minimum constraint version of the optimum. And once we've got all of the graph elements created, we can use figure.addTraces this time and add all of them in a list and add it to our figure. Now you can see that we have an unconstrained minimum, our equality constraint plotted in an orange line, and also a constraint minimum. And that's how you can plot constraint. Now in terms of the questions, first one, it says visually what does an equality constraint mean? An equality constraint basically, if you remember from our lesson, it basically means that it mandates all of the feasible solutions to be on this line. So only points that lie on this line would be considered a feasible solution. And therefore, our constraint minimum is also a point that lies on this line. And the second question was the geometrical relation between the constraint minimum and the unconstrained one. If you remember from our previous lesson, we say that the constraint minimum would want to get to the unconstrained one as much as possible because that would be the actual minimum value. So you can imagine it trying so hard to go from this point to this point until it gets to a point where it's closest to the unconstrained optimum. Then that would be the solution for the constrained optimum. Now, if we flip the question and ask if this was a maximization problem, where would the constraint maximum point be? Now, this is a question for you to think about, and then we'll see if you can answer it correctly in our next quiz. But some hints for you. If you remember from the earlier plot, we saw there's the unconstrained maximum here. So which point on this line do you think would be the closest point to that unconstrained maximum? Then that would be your solution. Let's take a look at inequality constraint. If instead the constraint above was actually an inequality constraint, so g equals x1 minus x2 less than or equal to 1.5, how do we visualize it? Well, earlier we talked about that our constraint has other kinds of arguments. For example, when we specify type equals constraint, we can actually also specify the operation, meaning the equality sign, or whether it is less than or equal to, or less than or equal. You can actually specify it here. So I can change the contour object, the constraint object that we created earlier using con.update. And then here I can change the operation to less than or equal to for my inequality constraint here. And then the name, I can also change it to simply inequality constraint as well. Then once I've updated this constraint, we can add the traces again to a new figure. And you can see immediately that the plot will have an inequality constraint shaded in the region. So this will be the infeasible region where you can't actually find any feasible solutions. And because this is still an active constraint, so the solution doesn't really change, it's still the same constraint minimum as before. Now, some questions: what is the maximum solution if this was a maximization problem in this design space? So because we can see that this area we can't reach because it is infeasible, our original unconstrained maximum actually lies in the feasible region. So that itself is also our solution if this was a maximization problem. So this would be the new optimum or maximum point if we are maximizing this problem with an inequality constraint. Now, if the constraint was actually greater than or equal to 1.5, where would be the shaded region and where would be the corresponding minimum point? Now, this is again a question for you to think about. But if you remember, we say that if the sign is flipped, so would the shaded region as well. So you can imagine it being flipped to the other side. And once that happens, you will see that this becomes the infeasible region and our original maximum point will no longer be feasible. So this is how we can visualize optimization problems, their objective contours and the constraints. And don't forget to answer the questions in the upcoming quiz. And yeah, I hope to see you in the next lesson after that.